Okay, good afternoon, everyone, or good evening, rather, I should say. Can I just get a thumbs up if everyone can see me and hear me clearly, please? Okay, perfect. Thank you. I've got some thumbs up. Okay, so apologies about the late start. I know we're running a couple of minutes behind. We had some technical difficulties, but everything seems to be up and running now. So for those of you who were here last week, Thursday, so we would have had a session together. My name is Dr. Dlamini, and we're going to be going through electrostatics again today. So again, at any point, please feel free to stop me. There's a fair bit more of you in the chat today. So if you have a question, you can pop it in the chat. You are more than welcome to pop it in the chat. We've got Apile, who is monitoring the chat. He's one of our senior PhD students. So he will answer your questions. And if I see your question, I'll also answer your question. So please feel free to ask your questions. So what I'm going to do now is I'm going to stop my screen share. Stop sharing my video, and I'm going to start up my screen share. And we are going to get on with the business of electrostatics, continuing from where we left off. And again, if I'm going too fast or too slowly, please stop me and let me know before I get too far ahead of myself. Okay, so I'm just starting up my screen share. Okay, can I just get one more round of thumbs up, please, if you can see that clearly if it's showing up on your side. Okay, perfect. And Tindiso, is that a hand up? Or is that your version of thumbs up? Okay, I think that was your version of thumbs up. Okay, so as I said, it's our second session on electrostatics today. So I prepared a couple of questions for us to go through, and it follows on from last week's session. If you missed the session last week, I've been told that at some point it will be posted on to the YouTube channel, at which point I'm sure the link will get shared out with all of you. So as I said, electrostatics. So the first problem we're going to cover today is one that comes up a fair bit. We've got 3-point charges, namely Q1, Q2, and Q3, and they are each carrying charges of +6 microcoulombs, -3 microcoulombs, and +5 microcoulombs. And they are arranged as shown in the diagram alongside. And we are also told that the distance between Q3 and Q1 is 30 centimeters, and that between Q3 and Q2 is 10 centimeters. So question 3.1, which is a very common question, which you'll see if you go through past papers, asks us to state Coulombs law in words. So again, if you were here last week, you would have gone through this, but I think it's instructive because I see several new names on the list. So it's instructive for us to go through this. So if you ever forget Coulombs law in words, you can always work it out from the equation, right? Because if you remember Coulombs law, we have that the force is directly proportional, or the magnitude of the force is directly proportional to the product of the charges, or the product of the magnitude of the charges. But you also know that the magnitude of the force is inversely proportional to the square of the distance separating those two charges. And so if you build this all together mathematically, we have that the magnitude of the force between 2-point charges is directly proportional to the magnitude of the product of the two charges and inversely proportional to the square of the distance between them, right? It's our inverse square law. And then the final step, of course, is we said that the force is equal to, we have our constant of proportionality, which I think you guys call the Coulomb constant, which is just K, Q1, Q2 over R squared. So if you ever forget the words, don't panic, because you can always use the mathematics to remind yourself exactly what Coulomb's laws say. So to put this all together in words, Coulombs law states the following. It states that the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. Okay, so that's Coulombs law in words. Now, it's fairly straightforward, and you can always work it out from the equation should you forget. So it's good to know both forms. Now, remember that in this case, this is just the magnitude of the force. But we know that force is a vector, and so force must have both a magnitude and a direction. So in this case, we use Coulomb's law in order to find the magnitude of the force. And then in order to assign the direction of that force, we use the convention that like charges repel one another, and that unlike charges attract one another. In other words, if my two charges are unlike, the force is attractive. If they're like charges, the force is repulsive. What do I mean by like? Well, like is positive, positive, or negative, negative. Unlike is if one charge is positive and the other charge is negative. Okay, so that's 3.1. It's a definition. It's one you should know. Ideally, you should know both the words as well as the mathematical form of the law. Okay. Now, 3.2 asks us to calculate the net force acting on this charge Q3 due to the presence of Q1 and Q2. Okay.
Yeah.
Someone's microphone is on. Can you please mute your microphones? Thank you. Okay, so we need to calculate the net force acting on charge Q3 due to the presence of Q1 and Q2. So how you go about this? Well, 3.1 is the hint. We're going to use Coulomb's law in order to get the magnitude of the forces, and then we're going to get the resultant of those two forces. So if I just look at the diagram quickly, using this sort of statement I've written in blue here, I know that like charges repel one another. So if I look at Q1 is positive and Q3 is positive, it means that those two are going to repel each other, which means that the force I expect it to be in that direction. Right? I expect the force to be in that direction. Likewise, if I look at Q3 and Q2, the signs are opposite, and so I expect it to be attractive, which means that my charge Q3 is going to be pulled towards Q2. And so what I expect before I even do a calculation, I can already sort of tell that what I'm expecting in this case is to have some sort of resultant force that's going to ultimately end up being in some direction, like the purple vector. Okay, so what we need to do is we need to calculate the red force, we need to calculate the blue force, and then we need to find the, Anele, please mute your microphone.
Shit.
Also, please refrain from swearing on the stream. Thank you. Okay, so I need to work out the red force, the blue force, and then look at the resultant. So we sort of have the directions already using this statement here. We've got our directions and we've sketched them onto the question because I'll redraw it in a bit. So how are we going to go about this? Well, we need to work out the magnitudes. And to work out the magnitudes or the sizes of the force, we're going to use Coulombs law, which is this K Q1, Q2 over R squared in general, right? And from this, I can work out the force on by Q1 on Q3, right? The force by Q1 on Q3 is equal to K, which I know, which is 9 times 10 to the 9. Q1 is, I should call this Q1, Q3, otherwise it gets confusing. So Q1 is 6 microcoulombs. So it's 6 times 10 to the minus 6 multiplied by Q3, which is 5 microcoulombs, which is 5 times 10 to the minus 6. And this is divided by the square of the distance between them, which is 30 centimeters. Remember to convert this to meters so that you're working in SI units. It becomes 0.3 squared. And in this case, I get that the magnitude of the force is equal to 3 newtons. Or in other words, the force by charge 1 on charge 3, the actual force is equal to 3 newtons, and it acts to the left. Or you can say to the west, however you prefer to write your directions. Likewise, I do the same thing to find this blue force, the force that 3 experiences because of 2. So it's the force by 2 on 3. And in this case, the magnitude of the force by 2 on 3 is going to be K, which is 9 times 10 to the 9, multiplied by Q2, which is minus 3. But I remember I'm taking the magnitude, right? So we take the magnitude. So even though it's negative, you disregard the negative sign when you're using Coulombs law. What your paper is this? Oh, sorry. Thank you, Erica. The paper is from 2020. I got the questions from 2020. I just noticed your question now, right? So it's going to be K is 9 times 10 to the 9. Then I've got 3 microcoulombs, which is 3 times 10 to the minus 6. I've got Q3 is 5 microcoulombs, which is 5 times 10 to the minus 6. And this in turn is divided by the square of the distance. Again, you need to convert this into SI units, so it becomes 0.1 squared. And in this case, if you put this in your calculator, if I've done this correctly, I should get 13.5 newtons. So that's going to be the magnitude of the force. The actual force itself, remember, because force is a vector, the force must have a magnitude in a direction. It's going to be 13.5 newtons, and it's going to be pointing downwards. Now, of course, depending on how you choose to give your directions, You could have called this west, and then this would just be south, but that is completely up to you. Okay, is everyone still with me at this point? Okay, okay, I've got 1 thumbs up, 2 thumbs up. Okay, cool, got a couple more thumbs up. So I assume everyone is with me. If you're not, please stop me either by unmuting or hinting in the chat. Why isn't it upwards? Okay, so it's not upwards because remember, I'm looking at what happens to charge 3 because of charge 2. We said in our rules for determining the direction that like charges are going to repel, meaning that like charges will push each other away, while oppositely or unlike charges or oppositely charged particles are going to pull each other towards each other. So they're going to attract. So in this case, I've got a charge here that is positive, and down here, I've got a charge that is negative, which means that if I'm sitting on this charge, I'm going to feel a pull that is going to be pulling me towards the negative charge because these two charges are opposite. In the other case, what I had was I had a positive charge here and a positive charge here. And remember that these two will always repel each other. So Q3 is moving towards Q2, yes. So the force is pointing from Q3 towards Q2 because Q3 is going to be attracted to Q2 because of the force. For the direction, you can write attraction or repulsion. That is also acceptable because you can determine, if you say attractive, it means towards, and repulsion means away from. So yes, Normanda, you can put it that way, should you so choose. Okay, so now that I've got my two forces, well, we still need to find the resultant, because remember, they want us to calculate the net force that is acting on this. Can I please explain? No, I'm still going through 3.2. We're not done yet. Let me finish it, and then I'll go through it one more time slowly, because we still need to calculate the net force. So far, what we found is we found the red force and we found the blue force, but what we actually want is the purple force, which is going to be the net force. So I'm just going to resketch this quickly because I don't want to keep moving the page up and down, right? So in other words, what I've got here is we've got this force that we said acts to the west, and it's got a magnitude of 3 newtons. I've got this force that acts to the south, which I'll draw in blue, right? And it's got a magnitude of 13.5 newtons. So I want the resultant between these two. So remember that to get the resultant, what I can do is you can join these head to tail. If I join these head to tail, it'll then give me the resultant. So I can shift this blue vector, right? I can shift this blue vector and attach it to the head of the red vector. Then what I have is that the resultant right? This black line here is then going to be my net force, or the resultant force. So I call it FR, or you can call it the net force F net. Remembering that this blue force is going to be 13.5 newtons, and that my two forces, or the blue and the red force, are orthogonal to one another. So to find the resultant, well, we're going to use Pythagoras. So the magnitude of the resultant, which is FR, is going to be equal to, say, the square root of 3 squared plus 13.5 squared. right? That's just Pythagoras. And this is then going to be equal to, I think, 13.83 newtons. Okay, so that gives us the resultant. I mean, that gives us the magnitude of the resultant. But remember that the resultant, they want the net force, not the magnitude of the net force, but they want the net force. And because it's a force, it must have a magnitude as well as a direction. So I'm going to pick this angle here. I'm going to call it theta. And from my trig ratios, I know that the tan of theta is going to be equal to 13.5, which is the opposite side, divided by the adjacent side. Tan theta is opposite over adjacent. So it's 13.5 over 3, which means that theta is going to be the inverse tangent of 13.5 over 3. Somebody's got their microphone unmuted. And if I do this into my calculator, I should get that this is going to be 77.4 degrees. Okay, another word of warning here is to please ensure that your calculator is in degree mode when you're doing this and not in radian mode. Rwandile wants to know, does it matter which angle I choose between the two? It does not, because you're going to see in a moment that when I give the actual force, I need to specify where I've taken my angle. So as long as you always specify where you take your angle from, then you should be fine. So to put it all together, the net force, which I don't know if you guys call it FR or FNet, but let's call it FR to be consistent or resultant, is going to have a magnitude of 13.83 newtons at an angle of 77.4 degrees below the horizontal. Or you can say, rather, if you don't want to say below the horizontal in this case, you can say, was it a south of west? So that's perfectly fine. Or you can say something like it's going to have a bearing of, what's this going to be? 192.53 degrees, if you want to quote your answer in terms of the bearing. Okay. Okay, there's a question on like charges. Okay, I'm going to cover that in a moment, because as I promised, I'm now going to go through this. So I'm going to go through the solution for 3.2 one more time. We've developed the solution. I'm going to go through it, but please keep posting your questions as they crop up. So this was the picture that I was given, and I've been asked to calculate the net force that's acting on Q3 due to the presence of Q1 and Q2. So remember that the net force, or the resultant force, is just, we sum up all the forces to get the net force. So in other words, we need to calculate the force that Q3 experiences due to Q1. Okay. We also need to calculate the force that Q3 experiences due to Q2. And then we need to take those two forces and we sum them up together to get our net force, or our resultant force. And in this case, that's this purple vector that I've sort of drawn into the diagram. Yeah, so that's our starting point, and that's what we're trying to do. So in order to get the magnitude of the force, we use Coulombs law. So Coulombs law is that F is equal to K Q1 Q2 over R squared in general, right? So what I'm going to do now is we take that and we use it to work out the rate force. So this first bit here, that first bit there is us working out the red force. F13 is equal to K, which is 9 times 10 to the 9, Q1, Q2 over R squared. Make sure that the R is in meters for the SI units, to make sure that we stick to SI units. Then comes F23, which is this blue force here, this blue arrow, the force represented by that blue arrow. And that force is F23, which acts to the south, right? And again, it's the same thing. The thing to be important, or the thing to note in this case, is that although the force is negative, right? See, the force is negative here. Not the force. Sorry, I'm so confused. The charge is negative. So even though the charge is negative, right? When it comes to applying Coulombs law, I only care about the magnitude of the charge. So don't put the minus sign in there. Just use the magnitude of the charge or the absolute value of the charge. Meaning if it's got a minus sign, I disregard the minus sign. How you fix the directions? Well, to fix the directions, we're going to use the fact that the like charges will repel one another. What does that mean? Well, repel one another means they're going to push each other away. So if this is a positive charge and this is a positive charge, the charge on the right is going to feel a force that wants to push it in that direction, and this charge is going to feel a force that wants to push it in that direction. So if the two charges are positive, they're going to have a force that wants to push it away from the other charge, acting along the straight line that joins the two charges. So if we look at what I've done here, I've got my Q3 and my Q1. The dotted line is the line that joins the two charges. And so my force is going to act along that line, but Q3, because Q3 is positive and Q1 is positive, they're going to push each other away. And that's how I know that Q3 is going to move to the left, or it's going to move in a westerly direction. Okay. When it comes to the other one, when I'm looking at Q3 and Q2, now I need to take into account this minus sign, right? This minus sign now becomes important because in this case, I've got a positive charge sitting here and I've got a negative charge sitting here, right? And what happens now is that like and like charges are going to attract. Okay, so you look at the sign of the charges if you want to find out. Yes, that's exactly it in the chat, Pila. So you look at the sign of the charges only when you want to find the direction. So in this case, this positive charge is going to feel a force pulling it towards the negative charge, and this negative charge will feel a force pulling it towards the positive charge. So because the signs are opposite, they're going to attract one another, right? And that's why I know that the force that the 5 microcoulomb charge experiences is going to be in the southerly direction. Okay, so that's how I get this red expression and this blue expression. But what we want is the resultant or the net force. And so we need to draw our vector triangle. And I hope everyone is familiar with vector triangles, but we need to draw our vector triangle. Who's unmuted here? Tabile. Okay, so there's my vector triangle. I've got the red force pointing westwards, and I've got the blue force pointing southerly, in the southern direction. To find the resultant is a simple application of Pythagoras. So it's a squared plus b squared is equal to c squared. Take the square root and you'll get c. That gives us the magnitude of the resultant. And then I work out my angle. In this case, this is my theta. I saw a question, I think Apila answered it, of why do I say below the horizontal? Well, in this case, because if we look at this dashed line, that dashed line is the horizontal line and my angle is measured beneath. If I start from here and I end here, my angle is measured beneath the horizontal. Okay, is that clear? Or is there something else you'd like me to go over? Or is there something that I need to clarify, rather, I should say? Okay, I see a thumbs up. Okay, I see several thumbs up. Okay. Okay, I've got more than 10 thumbs up going up in the chat. So I hope we are fine with that kind of question. So let's go on to the next question that I prepared. And this one that's actually a question I like very much. It's a good question because it brings in some of your mechanics. It's not just electrostatics, it's a bit cross-disciplinary. So in this case, I've got a very small graphite coated sphere, P, which is rubbed with a cloth. And afterwards, it is found that the sphere acquires a charge of +5 microcoulombs. So 5.1 asks us to calculate the number of electrons that have been removed from the sphere P during the charging process. So again, remember that when it comes to electrostatics, the base unit of charge is the just got one more question with question 3. So let's just wrap it up. Would it matter if you draw the south arrow to on the right instead of on the left in question 2? Okay, regarding the arrows, would there be an issue if you draw your south arrow on the right instead of on the left? Do you mean, okay, if I've understood you, sorry, do you mean would there be an issue if I had something like this? Yes, there would be an issue because then your angle would be wrong. Remember, Erica, well, I suppose strictly, actually not really. If you do it this way, so if you had to do it this way, you wouldn't be able to use Pythagoras. You'd have to use the parallelogram of vectors, which remember involves you draw this dotted line, there's this dotted line here, and then your resultant goes across the parallelogram of vectors. What you can't do is you wouldn't be allowed to do this here. You wouldn't be allowed to say those two are added together and that this is my resultant. And the reason that you're not allowed to do that is, if you remember, when it comes to vector addition, the general rule is that we join our vectors, or we add our vectors. We join or add our vectors head to tail. Head to tail. And the one exception to this is the resultant vector is joined head to head and tail to tail. So here, for example, you'll see that if this is let me use a purple pen so that I don't write over this. So if this is the tail of the red vector, there's the head. So that means that the tail of the blue vector, which I want to add to the red vector to get the resultant, the tail of the blue vector must be at the head of the red vector, right? And the exception to this is the resultant vector, which is joined tail to tail and head to head. What you could do, if you really wanted to, is rather than draw it this way, you could keep your southern pointing vector and you can draw this red 3 Newton vector along the bottom rather than along the top. So this would be 13.5. And in this case, it'll be tail to tail, head to head would give me my resultant vector. Okay, I hope that that clears that up, Erica. Okay, perfect. On the part of the bearing, it's just a different way of expressing your angle. So remember that what you're essentially going to do is, okay, so here's my vector. If this is 77.4 degrees, right? This is 0 degrees on a bearing. This is a bearing of 90 degrees or eastwards. This is a bearing of 180 degrees. So I measure my bearing clockwise. So basically the bearing is going to be this angle here. And how I get this angle here, it's going to be 270 degrees minus this red angle here. So minus the 77.4 degrees. Is that okay, Clive? Or do you want me to go deeper into that? Okay, perfect. Okay, so remember that between below the horizontal, south of west, or as a bearing, it's up to you which one you are comfortable with. Okay, Oppo wants me to go deeper. Okay, I'll go deeper just quickly so that we can make the next question. So when it comes to your bearings, bearings are just a different way of giving a direction. So this would be 0 degrees, bearing of 0 degrees. This would be 90 degrees, 180 degrees, and this would be 270 degrees. So if somebody says that you're walking on a bearing of 45 degrees, it means that you are going to be 45 degrees of north. Right, your bearing is 45 degrees. So in this case, what I know is that my angle theta is 77.4 degrees below the horizontal, right? Meaning that there's my resultant there. And this angle here is 77.4 degrees. But if I want to give it as a bearing, I need to start on north and I need to work my way down. So I've got 90 degrees, I've got 180 degrees, and I've got some portion that is left over there, right? But what I do know is that if I were to take the purple bearing, right? My purple bearing would be 270 degrees. So if I want to find my blue bearing is going to be the 270 degrees minus the 77.4 degrees. Okay, Oppo, does that make sense? I don't know your real name. I assume that's your phone name. Okay, I seem to have a thumbs up. Okay, cool, perfect. Okay, so let's move on to the next question. So here's the next question, what you're going to do today. So I've got a very small graphite coated sheet rubbed with sphere. P is rubbed with cloth, and it's found that the sphere acquires a charge of 0.5 microcoulombs. And they want us to calculate the number of electrons that have been removed from the sphere P during the charging process. Okay, so with this kind of question, you need to remember when it comes to measuring charge, that you can divide charge up into certain quantized chunks or into certain bits, and it turns out that it's the charge on an electron. So when you have we have two types of charged particles. Essentially, we have the electron, which is the symbol E, and it's got a charge of minus 1.6 times 10 to the minus 19 coulombs. And we also have protons, and they've got a charge, positive charge of 1.6 times 10 to the minus 19 coulombs. Okay, Junior says he's having an issue hearing me. Can everyone else hear me? Okay, Junior, I've got thumbs up from the rest of the crowd, so I think it's on your side. just try raise your volume or maybe try to disconnect and reconnect. But apologies about that. If you've got an issue, as I said, the recording will be posted, but if it's best if you can at least join the audio on your screen. Okay, so we've got these two charges. And basically when we say something has got a charge of, or a neutral charge, it means you have as many positive charges as negative charges, then you'll be neutrally charged. If you've got a charge of plus 0.5 microcoulombs, it means that you've lost some electrons. If you've got a charge of negative 0.5 microcoulombs, it means that you have gained some electrons. And the simple way that we can say how many electrons you've either lost or gained is we use the simple result that the total charge is the number of electrons multiplied by the charge on a single electron. Okay, so the total charge is the number of electrons multiplied by the charge on a single electron. And we use the magnitude. Okay, so notice I'm not going to use E as negative 1.6. I'm just going to use the number, the magnitude. Erica, I believe again that this was 2020, and where will the recording be posted? I have no idea. At some point, somebody's going to post a register where you're going to sign the register, or the register is actually up in the chat. I think Dogozo will come back and repost the register, at which point, I think once the videos are up on YouTube, the link will be sent to everyone who attended the session, I think. No promises. So in this case, to calculate the number of electrons, we just rearrange this equation. So the number of electrons, the number of excess electrons, I should say, so it's the number of extra electrons that I've either gained or lost, is going to be equal to the charge, Q, divided by the charge on a single electron. So in this case, the total charge on my sphere is 0.5 microcoulombs, which is 0.5 times 10 to the minus 6. And this I divide by the charge on a single electron. Thank you, Ndogozo. So Ndogozo has reshaped the register. So if you haven't signed it, please make sure you sign it before you go. Right, so it's the total charge, which is the 0.5 microcoulombs. And I divide this by the charge on a single electron, which is 1.6 times 10 to the minus 19. And this tells me that the number of electrons that I've actually lost is 3.13 times 10 to the 12 electrons. Okay, now remember, if my sphere had had a negative charge, then that would have been the number of electrons that I had gained. So that is fairly straightforward, and it's a fairly easy 3 marks to obtain. It does crop up from year to year, sometimes once or twice. Why isn't the 1.6 times 10 to the 19 negative? It's a good question. So the reason that it's not negative in this case is simply because I'm looking for the number of electrons that I've lost. Now, it would be different if I wanted the charge, right? If I want the magnitude of the charge, then all I would use is Q is equal to NE. But if I want the actual charge of the sphere itself, if I tell you that a sphere has gained 3.13 times 10 to the 12 electrons, what is the charge on the sphere? In that case, you would have to use the sign. If I tell you that it's lost, then what you'd actually have to use is essentially that Q is equal to NP. Let's remind this here, sorry, for the electron symbol. So in this case, it's not negative because I'm using the magnitude, simply because I just want a number. I just want the number of electrons that are involved. Okay, so that's 5.1. 5.1 is straightforward. Now the story changes with 5.2, because what happens now is that the charged sphere P is then suspended from a light inextensible string, another sphere R with a charge of minus 0.9 microcoulombs on an insulated stand is brought close to sphere P. And as a result, sphere P moves to a position where it is 20 centimeters from sphere R as shown. The system is in equilibrium, so that's important, right? So the system is in equilibrium, and the angle between the string and the vertical is 7 degrees. Do we always use this formula? Pretty much, yes, Tabila. If you want to calculate the number of electrons removed or added, then this is the equation that you're going to use. N is the number of electrons, Q is the charge, and E is the charge on a single electron or the charge on a single proton, or the magnitude of the charge, I should say. I need to be strict about what I'm saying. It's the magnitude of the charge. But yes, that is the equation that you should always be using to calculate the number of electrons on anything. So 5.2 asks us to draw a free body diagram showing all the forces acting on sphere P. Okay, so this you should all be familiar with, I think, from your mechanics. So there is my sphere P. So the forces acting on P, I'm going to have the weight, which always acts downwards. 082 says, okay. Okay, let me see these questions. Okay, when do we use the P plus in the formula? In this case, you never really use the P plus in the formula, because you say that rather than using P plus, we say that we work out the number of electrons that you've lost. So instead of saying you have 3.13 times 10 to the 12 protons more, we say that you've lost 3.13 times 10 to the 12 electrons. Now, the reason why we always refer it in terms of electrons is because remember that electrons are what's free to move in your conductors. So in your conductors in general, you have your protons, which are more or less fixed in place, but within these, there's this delocalized sea of electrons. And so what actually happens is when things are getting charged up, it's the sea of electrons, because they're delocalized and they aren't being held together by strong forces. The electrons are free to move around. And so it's the electrons that move to something, or so they move away from you, or they move from some other object onto your object, but it's the electrons that move. And that's why we tend to express or write this in terms of the number of electrons gained or the number of electrons lost. Y times 10 to the minus 6 times 10 to the minus 6, it's micro. So this symbol here is times 10 to the minus 6. Okay, so in this case, back to my free body diagram, I've got the weight, which I call W. Now, we all know the weight W is equal to mg. Some people call it the force due to gravity. Some people call it FW. Okay, doesn't matter which one you call it, as long as you are consistent with what you call it. Right, so in this case, my weight is equal to mg. I'm going to call my weight W. I'm going to have a tension force, right? And the tension force is going to be pulling along the string in this direction. And lastly, remember that sphere P is positively charged, right? In other words, this has got a positive charge, and I'm told that sphere R has got a negative charge, which means that there's going to be an attractive force between P and R, right? There's an attractive force between P and R, which means that sphere P is going to feel a force pulling it towards R. So in other words, there's going to be a force that pulls it to the east or to the right. and I'll call this Fe. Okay, again, this is just my naming convention. It's the electrostatic force, it's the Coulombic force. So sometimes people will say, I'm saying Fe because I like to think of it as the electrostatic force. And some people call this FC, where C stands for Coulombic because it's Coulombs force. What you choose to use, I suppose, is up to you. But remember, again, just please be consistent. And in this case, there is not a normal force because remember that this is suspended. So there's no normal force. These are the only three forces that are acting. That's the tension in the string, the electrostatic force, and the weight, because it's suspended. So if this is my P, I've got a tension acting upwards and the weight acts downwards. These are the only two forces if I remove R. Because I've introduced R, R has this attractive potential, this electrostatic force, and that sort of pulls the sphere P to the right. Okay, so that's 5.2. That's the free body diagram. Okay, what's next is State-Coulombs law in words. Okay, so this one we've gone through because I think it's similar to what we saw in the previous question, but again, you know, it's the magnitude of the electrostatic force by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Okay, so I'm not going to go through that in detail because I think we're all familiar with that from the previous example. Okay, so a couple of questions quickly before I move on to 5.4, because I assume everyone is fine with 5.2. So the question is, what reasons can you give if we are asked to explain why the string is light and inextensible other than for calculation purposes? Okay, so the reason that the string should always be light and inextensible is that if your string has got mass and if your string has got elasticity, so in other words, if I can stretch my string, then I need to work out bring in the fact that the string stretches and deforms, which then brings in Young's modulus, and it becomes a more complicated problem, right? So you don't want to account for the stretching in the spring, and I don't want to account for the fact that the string must have a mass, and so I need to include the mass of the string in the calculation. And so to simplify the problem, because we're just starting out, we consider these light, inextensible strings. If you actually end up at UKZN or some university studying physics, by the time you get to second year and third year, actually even the engineers, you start to model the real world. And in the real world, obviously you know that strings aren't this perfect light, inextensible thing. And you start to factor that into your calculation. But for now, at the grade 12 level, we don't want to introduce that complexity in. Normonde is, what if I write FR on P instead of FE, I assume? That would be fine. the force of R on P, instead of calling it FE, if that's what you're meaning, Nomonde, that is perfectly acceptable. Yes. Okay. So that's 5.2 and 5.3. So 5.4 asks us to calculate the magnitude of the tension in the string. Okay. So what I want to find is the magnitude of this tension in the string. Okay. So the important thing that's going to help me out here is the fact that the system is in equilibrium. So if you think back to your Newton's second law studies, if a system is in equilibrium, what does that mean? It means that the net force acting on the system must be zero, right? So when you see the word equilibrium, it means that the net force must be equal to zero. So this comes from Newton's second law, that the net force is equal to zero at equilibrium. Okay. Isn't FR the frictional force? Okay, you guys talking about, you're talking about FR. She's talking about saying FRP, the force on R, the force by R on P is what she means. I hope that clears that up. So usually they use FR like this here for friction, but not in this case. What she's talking about is something like this here. But in general, remember, you're free to name your forces however you feel. Completely up to you, as long as you're consistent. So Newton's second law says that the net force must equal zero at equilibrium, right? But we can go one step further. We can apply Newton's second law in the x direction, and we can apply Newton's second law in the y direction. Please let me know if my notation gets confusing or if it's not quite what you're used to seeing. And I will try and adjust to something that you are used to seeing. So the sum of Newton's second law in the x direction says that the net force in the x direction must be equal to zero at equilibrium. And the net force in the y direction must be equal to zero at equilibrium. Okay, so if I look at my force diagram, right, I'm going to pick directions to be positive. Okay, so for reasons I myself am not even sure about, I couldn't tell you if you asked me, I always pick up as positive. So y in the y direction, up as positive, and in the x direction, to the right as positive. Okay, again, remember that the physics doesn't depend on the direction that I pick. The direction that I pick is something that is completely arbitrary. It's completely arbitrary and it's completely up to you. But once you pick it again, you just need to be consistent. Consistency is probably the most important thing in this case. So if I look at this, well, the electrostatic force, right, my FE only has components in the x direction. My weight only has components in the y direction, but my tension force is going to have a component in the x direction and a component in the y direction, right? It's going to have a component in the x direction, which I will call Tx, and it'll also have a component in the y direction, which I will call Ty. Right? Now, again, it's important. I've drawn the components in dotted lines because remember, you shouldn't duplicate your forces on your force diagrams. The other piece of information I'm given is I know what this angle is here. This angle is 7 degrees. So if I use Newton's second law is that the sum of the forces must equal zero. So by applying Newton's second law in the x direction, so this is question 5.4, sorry, that should have been moved down. Let's see if I can move it down. So we're doing 5.4, writing in the wrong place. Okay, sorry about that. So if I apply Newton's second law now in the x direction, so applying Newton's second law in the x direction, I have the electrostatic force, Fe, minus the x component of the tension must be equal to 0. Likewise, if I apply Newton's second law in the y direction, I'm going to have Ty, because I've chosen up as positive, minus the weight must equal 0, which looks promising, right? It looks promising. The only issue here is, well, what are Tx, Ty, and Fe? Well, to find Tx and Ty, we're going to use some trig, right? So if I look at the sine of 7 degrees, right? Remember, sine is opposite of a hypotenuse. It's equal to the opposite side, which is Tx, over the hypotenuse, which is T. So from this, I get that Tx is equal to T multiplied by the sine of 7 degrees. Likewise, if I look at Ty, Ty is adjacent to the angle. So adjacent sounds like a cosine, so it sounds like cos. So the cos of 7 degrees is equal to the adjacent, which is Ty, over the hypotenuse, which is T. So in other words, Ty is going to be T times the cosine of 7 degrees. Okay, so that comes from the trig ratios. Fe, I also don't know, but I can work out what Fe is, right? Because I know what the charge on P is, I know what the charge on R is. And so to work out what Fe is, I can simply use Coulombs. Okay, I'll explain it now, or wait to. Right, to work out Fe, we're going to use Coulombs law. Right, so Fe, so to work out what Fe is, it's going to be Coulombs law. It's going to be K QP QR over R squared. Okay, which just comes from Coulombs law. Okay, now I'll explain this again. Let me get a purple pen so it doesn't get in the way. So essentially what you've got here is I've got this triangle, right? And the sides of my triangle, I've got T, is the hypotenuse. There's my right angle. On this side here, I've got Tx. And on this side here, I've got Ty, okay? And I know that this angle here, let me call it theta for now, right? So you know from your trig ratios, what's it, that some old hens cackle and howl till old age. So the sine of theta is opposite, is the opposite side of the angle divided by the hypotenuse. Cos theta is equal to what? The cos of theta is the adjacent side, so the side next to the angle. So this is my theta, the side next to theta is going to be, well, let's call it adjacent. It's the adjacent over the hypotenuse, and tan theta is the opposite side divided by the adjacent side. Okay, so those are the definitions of my trig ratios. So here's my angle, theta. In this case, theta is 7 degrees, right? So if I do sine of theta, the sine of theta is the opposite side, which is Tx, divided by the hypotenuse, which is the tension, T. Then I can multiply both sides of this equation by T, and that'll tell me that if I multiply both sides of this equation by T, I get that Tx, or T sine theta, is equal to Tx. And in this case, theta is 7 degrees. So it's T sine 7 is equal to Tx. And then I'm going to do the same thing with Ty, but I notice if this is my angle theta here, then Ty is the adjacent side. So I've got adjacent and hypotenuse, and adjacent and hypotenuse is the cosine. So in this case, I end up with a cos theta is going to be the adjacent side, which is Ty, over the hypotenuse, which is T, which means that T cos theta, or T cos 7 in this case, because my angle is 7 degrees, must be equal to Ty. Is that all right away too? Okay, perfect. Okay, so yeah, so it's just the applying your trig definitions onto this triangle that we formed, into this vector triangle that we have formed. Okay, so now we're good to go. Now we have all the pieces of the puzzle. So now we need to put them together. Okay, so if I look at the question, I'm not told what the mass of the sphere is. I do not know what the mass of the sphere is. If I don't know what the mass of the sphere is, I can't work out the weight of the sphere, which means that if I use Newton's second law in the y direction, it's going to give me some problems, right? If I use Newton's second law in the y direction, it's going to give me some problems because I have no way at the moment of calculating this weight. So what I then do is the following. I'm going to use Newton's second law in the x direction. So Newton's second law in the x direction is Fe, which is this mess here. So I get Fe, which is K QP QR over R squared minus Tx. But what is Tx? Tx, we've all agreed, is T sine 7 degrees must equal 0. The reason it must equal 0 is because we are at equilibrium. So it's Newton's second law in the x direction applied at equilibrium. Right? So you can rearrange this. So I'll get that T sine 7 degrees is equal to KQP QR over R squared, which means if I make T the subject of the formula, I get that the tension is going to be K QP QR over the sine of 7 degrees multiplied by R squared, right? And what is this equal to? Well, this is equal to now 9 times 10 to the 9. QP is 0.5 times 10 to the minus 6. QR was 0.9. All right, 0.9. 0.9, yes. 0.9 times 10 to the minus 6 divided by the sine of 7 degrees multiplied by the distance between the two spheres, which is 20 centimeters. Remember to convert to meters. So it's divided by 0.2, and don't forget to square it. And if you do this, this should come up to, if I've done this correctly, somebody can check, this should come up to 0.83 newtons as the magnitude of the tension. So again, remember that in this case, QR, we take the magnitude when we use the Coulombs law. It's the magnitude. So you'll see I haven't used the fact that QR is negative. Hasn't been used at all in calculating the magnitude of the force, but it was used in obtaining this force diagram, the force diagram, because I knew that this force must be acting to the right because it must be attractive because of the signs. Okay, are there any questions on that? Okay, no questions. Okay. I'm sorry we started a bit late today. As I said at the start, we had some technical difficulties, but yeah, but that's going to be it for today's session. I've been told that tomorrow Ursula is going to be running another mechanics section. So we've got another session tomorrow on mechanics. Otherwise, that's all I've prepared for you for today. Let me stop my screen share for a moment. That doesn't seem to have worked. Where is this? Ah, there we go. Okay, so that seems to be it. Okay, I'll answer your question now, Erica. So Erica's got a question in the chat. That's all I've prepared for today because we're out of time, but I'm going to hang around for another 5 or so minutes answering questions. So if you've got your questions, you can still put them in the chat. Please don't forget to sign the register because the register helps us keep track of everyone. And I will try and ask the person who coordinates this program, this helpline, to make sure that you all get an email notification once the video is posted. And if they don't post the video on YouTube, I'll ask them to at least email you a copy of the video where you can find the video. So let me just go back to my screen share. And let's see what Erica's question was. Okay, please resend the register. Okay, Apila, if you're still on here, can you please just go up in the chat and copy and paste the link for the register, please? Oh, Ndogozo's already on it. Don't worry, Apila. Thank you, Ndogozo. Okay, the register has been resent. Again, it's very important to keep the program running for the duration of the year. So where's Erica's question? If you decide to change the subject of the formula at the beginning, okay, so if you decide to change the subject of the formula at the beginning, which beginning do you mean? Just give me a hint here. Do you mean at the beginning here? Or do you mean right up at the beginning when we first state Newton's second law? Oh, sorry, there's also a second link from Dogozo that's for feedback and evaluation. So for feedback and evaluation, please follow the link. Please, I value your feedback personally on a personal note. I use your feedback to try and tailor my sessions. So the more detailed feedback you can give me, the better it would be. So please make sure that you just take the 5 minutes or so it takes after the session to get the feedback through to me. It does help me quite a lot. By where your arrow is, okay, perfect, Erica. Yes, no, there is no issue. You can change the subject of the formula from there. You can change the subject of the formula at any point. What my suggestion would be, or if I were to give some advice, would be don't put in numbers until the very end. It makes it easier to get part marks if you carry symbols, because with symbols, it's easier to spot your mistake and it's easier to try and follow what you're doing. So as you've seen, as I've been doing the problems, I tend to not want to stick in numbers straight away. I like to wait until the very end to stick in my numbers. So Owetu, Dogozo has come back to you in the chat. Life Sciences is going to be on Friday from 6 p.m. Tomorrow is going to be a mechanics session with Ursula. Okay, I hope that that is clear. Are there any other questions? You are welcome, Erica. Okay, if there are no more questions, I'm studying the chat. Apila, is there anything that's come up on your side? You can just type it in the chat if there's anything that's come up that hasn't been answered, or if we're all good.
For now, there's nothing.
Okay.
Yeah.
Perfect. Okay, that's perfect. Okay, good then, guys. Thank you so much. Again, sorry we ran a bit late, but I hope most of your answers or your questions were answered. If you look at the flyer that you used to register for this Zoom link, there's an email address associated to that. You can please send your questions to that email address during the week. And depending on the questions I get the next time we have a session, I will address those. But there's usually a tutor or somebody who mans that address. So you can also ask for help via that avenue. Otherwise, thank you very much for attending. Thank you for being interactive. And I hope I catch you on the next one. Enjoy the rest of your evening. Cheers, everyone.